Welcome to yet an exciting educational video brought to you by Christ-like Tutors. So today we'll be looking at MTH 112, Module 4, Unit 3, Techniques of Integration. So we'll continue with the series of integration, differential calculus for this course. And by the end of this course, we are looking at integration by parts, partial fractions, trigonometric integrals. At the end of the lesson, you'll also be able to use integration by parts effectively for products or functions, breaking rational functions into partial fractions and integrate them. Thirdly, we can evaluate common trigonometric integrals using identities and substitution. Fourthly, recognize the structure of problem and choose the correct technique. And lastly, solve examples and attempt TMA style questions. So sit tight as we dive into this video. If you're not yet subscribed to our channels, kindly subscribe to Christ-like Tutors and share with friends so that these videos will get to them. So we dive in. Okay, so recall from product rule, when we are to differentiate with product rule, remember you are having two functions that are multiplied themselves. So if I have d dx of, let's say, these two functions, u and v, remember, the product differentiation will be this that is u dv plus v, then du. Remember this formula for product differentiation. And we know that integration is anti-differentiation. That means you need to differentiate this one back to get this one. So if you rearrange this by way of integration, you see that if I put integral d dx u v and integral u v prime plus integral v u prime, to rearrange this, you see that I'll take this one to be the subject. So I have, so when this one becomes subject, it becomes, first of all, this and this will cancel because this is integral and differential. So it will cancel. What I have left here is uv, right? Then I will now say integral u dv, because this prime is dv, right? Then plus integral v du. This one can come and join this one here. So I have uv minus integral v du is equals to integral u dv. Or I can come and say, I can put this one as on this side, integral u dv is equals to uv minus integral v du. So this is general formula for integration by parts. At this point, we are to split whatever you are given to have this expression. Okay. So, but then if you are given a product to integrate, you will need to choose which part is u and which part is the v. And there's a rule for us to choose a part of the integrand to be u and the rest to be the v. We don't just go ahead and just integrate like that. We need to carefully observe the expressions, the product of those two functions, and know which one can take the part of u, can become u for easy integration. To the part that will become u and the part that will become the v. Okay, so we have the helpful memory device or mnemonic to choose the part of the integrand that will be u, from the expression. Recall that we said that integration by part is integral v du is equals to, or let's say u dv, yes, is equals to uv minus integral v du. So it is u dv is equals to uv minus integral v du. So if you are to integrate these together, the two expressions, u part or the dv part, you need to choose which of the expression or the functions in the product of functions you are integrating, which one is u and which one is v. Now the formula or the mnemonics is to go through this. So first of all, you check, this is late, L-I-A-T-E. So the L stands for logarithms. So you check the two expressions or function of x, which of them has logarithm. If you have a logarithm, then you choose that one as u, then every other thing will be dv. So that's the first one. If you don't have logarithm, the next thing you look at is inverse trigonometry. If you have an inverse trigonometry in that expression, that's the next order, you choose u as that expression, So u takes inverse trigonometry, and every other thing, every other one under it should be dv. Or if you don't have inverse trigonometry, the next one is algebraic. That is, if you have powers of x, x squared, x cubed, and so on. So you choose u as the algebraic one, and every other thing will be dv. The next order of priority is trig, and finally exponential. So you look at it this way, late. So L for logarithm, I for inverse trigonometry, A for algebraic expression, T for trigonometry, and E for exponential. So we're going to be applying what I just explained here for any of the problems that we are. So for instance, now if I have this expression, integrates x dot e exponential x dx, right? So you see that there are two functions here. This is a function of x here, and this one is a function of x here. So which one is u and which one is dv? That is from this formula. Which one is dv? So we've got to look at all this and see that, oh, I don't have logarithm in these two. I don't have inverse trig in these two, but I have algebraic expression, which is x raised to the power 1, right? So my x, let u will be x, and dv will be exponential x. That is the way we'll choose them, so we can apply this formula. So let's quickly solve this and see how it plays. So we are told to integrate this. The first thing we have to do is to identify that these functions is a product of two functions of x. So this is the first function of x, which is x, and second function of x is exponential x. Now, this is integration by parts. Okay, so the formula is, if you have this formula, integral u dv, right, is equals to uv minus integral v du. Just know this formula. It came from the anti-differentiation of product rule. So that's how product rule is the opposite of integration by part. This one came from that way. If you integrate the result from product rule back, you will see that this is what it gives you. So this is the formula, but we need to identify which part is u here and which part is v here. And I gave you this late as the way of knowing it, where L is logarithm, inverse trigonometry, algebraic expression, trigonometry, and exponential functions, right? Okay, so I see that I don't have log, I don't have inverse trigonometry in this expression, but I have algebra. So this algebraic expression, x, so let this u be x, and dv part is the other one, exponential x. So I'm going to just put everything here in this expression. So I have the answer, that's integral u dv, that's the answer, is, now, what is my u? My u is x, right? And my v is dv. That is, I'll integrate this one. This dv, that's the differential. To get v is to integrate this one. if I integrate this one, I still get exponential x, right? And the x, du is, I differentiate this one, and du is 1. You understand? Okay, so I continue. So I say that u is x, right? Then v is exponential x minus, then integral. V is exponential x and du is 1, right? Okay, so having gotten that, I will now go ahead and complete this expression. So I have x e exponential x minus, okay, integrate this one again. If I integrate this one again, I will still get exponential x, then plus c. So this is the answer. This is the answer. So we have another example on the board. You say integrate x cos x dx. So again, it's by inspection. You see that we have two functions here. Okay, so but you expect again to see there are two function of x. That is, you have x as one of the functions and cos x as the other function. So which one is going to be our u and which one is going to be our dv? Remember that the formula is integral u dv is equals to uv minus integral v du. So our question again is which one is going to be v, u or v? There's a process for choosing v. One will have chosen our v, every other part of that equation or that expression will be u or the v, sorry. We are choosing our u following this late. It's an acronym that tells us the order we are choosing the expressions. The order we are choosing the expressions. Where L here is logarithm, I is inverse trig, then A is algebraic expression, T is trigonometric identity or ratio, then this is exponential functions, right? Okay, so just remember this mnemonics. So from here, I see that I don't have logarithm here, I don't have inverse trig here, but I have algebraic expression. So x is algebra and x will be u. So let u be x and du is equals to 1 then dx, right? Because du dx is 1. If I differentiate x, I get 1, right? So then the next one is if u is x, the remaining thing here is v, dv, right? So dv is the same thing as cos x dx. So I'm choosing u and dv. I can from there get what dv is. What v is. From here, if I differentiate, if I integrate dv, I will get v, right? So my v will be sine x from integration, from differentiation. My v will be sine x, right? Okay, so now I haven't gotten these 4 things. I'm going to put them in this expression. So the integral u dv will now be my u here is x, my v here is sine x, then minus integral, I'm following my formula, then v from here is sine x again, and du is dx. So I just continue and say x sine x minus, if I integrate sine x, what will I get from all our discussions on integrals? If I integrate sine x, I'll be getting plus cos x, right? Then plus c. Okay, so I have final answer x sine x plus cos x plus c. That's the integral of this particular function. So we'll go into the next one. Okay, so we have this on the board. Integrate ln x. You'll be wondering, this ln x, is it two functions that are there? We're going to be using integration by part for this one, and there are two functions there. And the functions are 1 and ln x dx. These are two functions. So again, using late to determine which of this function is u and which one is dv, knowing that our formula is integral u dv is equals to uv minus integral v du, right? So we want to know which one is u here and which one is dv here. We are using late. Remember, L stands for logarithm. It's just like what Bodmas does to mathematics, general maths, arithmetics. That is what this late does to integration by parts. It just shows you the order we are going to apply the choosing of u, which function we take u. So I have logarithm, I have inverse trigonometry, I have algebraic expressions, I have trigonometry, and I have exponential functions. So from here, top off, you see that I have ln x here. So u is ln x. So logarithm of x, natural log of x, right? And dv is 1 dx. How? Because dv dx is equals to 1, right? But we are looking at dv, not dv dx. dv dx is equals to 1. That's what dv dx is. But I'm looking at dv dx, right? But I will say dv is equals to 1 dx. So it's dx that is dv. Okay, so I've gotten these two. Now, what about the differential du dx? What's du dx? If I differentiate this one, I have 1 over x. Ln x, differential is 1 over x. Of course, it's du I'm looking for. So this x, the x will come here, right? Okay, so I've gotten du. What about v? V now is the integral of this. If I integrate 1, I will get x. So my own is to also find all these 4 parameters so that I can put them in this place, put them here. The first thing you do is always to write out your formula, then choose your u from late. Once I've chosen your u, then you now apply everything else as dv, right? dv. All right, because there's a 1 here and there's a dx here. So every other thing here is dv, right? Okay, so du again is the integral differential of this, and v is the integral of this. So I will just put everything here. uv, what is u? U is ln x, right? And v is what? What's my v? V is x. So I can put x in front, right? Minus, then integral. V again is what? X. And du, what's du? 1 over x dx. So from here, this can cancel this. So I'll say x ln x minus integral of 1 dx. So x ln x minus, if I integrate 1, I'm going to be getting x plus c. So this is the answer for this integral. This is the answer for this integral. So integration by parts is really very, very interesting. All you have to do is to first of all identify which part is u and which part is dv. You use your late acronym to get the order in which you will choose what u will be, and you will get all the other parameters, plug them back into the equation or into this expression, and now get your final answer. We're going to be stepping a little bit further to look at partial fractions. So when the integral is a rational fraction or a polynomial divided by another polynomial, we often break it into simpler fractions. So let's dive into partial fractions. Okay, so now we're going to be applying what we learned in partial fractions and know how to integrate by partial fractions. Okay, this should be integration by partial fractions. Okay, so if, for instance, I have these functions, p as a function of x divided by q as a function of x, we can split this into partial fraction. Split into partial fractions. How do we do this? How do we do this? For example, if I were to integrate 5 all over this open bracket x plus 1 and another one x plus 2 dx. If I were to integrate this, you see, I need to split this into partial fractions so that I will have this become 5 over x plus 1 x plus 2 now becomes in the form of a over x plus 1 plus b over x plus 2. You see what happens here? I want to split this fraction into two fractions, right? Into two fractions that if I add this fraction together, it will still give me this. But my dilemma is to know what the denominator of this first part of the fraction will be like, and what, sorry, not denominator, numerator of this first fraction will be like that, what a will be and what b will be. That's why I chose two unknown things. So I need to know what a is and what b is. So the first thing to do is to multiply each term by what I have here. So it's the same thing as saying 5 is equals to this a multiply this part of the fraction. That is, multiply the conjugate of this denominator, a into x plus 2 and b into x plus 1. I'm just trying to be fast here. But what happened? What happened between here and this line is that I just multiply each of these terms by this denominator here, so that this one can become 5 only. Understand? So if I multiply this by the whole of this, I will get 5. If I multiply this by this denominator here, I will get this one will cancel this one. I will now have a times x plus 2. And if I have this multiplied by this denominator, I'll be having this one cancels this. I have b into x plus 1. So this is what I have here. So at this point, by inspection, I'll say, I want to see what I will do to one of these parts. This first term here. There are 3 terms here. This term that is standing alone outside, this one is a clear term, is a 5. But here I'm having x and I'm having a. Understand? If I want to make this term to become 0, what will I do to x? If I say let x be minus 2, let x be minus 2. So that if I put minus 2 here, minus 2 plus 2 will be 0. So that if this is 0, all the whole term will be 0. And this one will have something. So let's go with that. Let x be minus 2, right? My goal is to find what a and b is. So the first thing is to write this one first. Look for something to make x be so that everything will be 0. And that thing is minus 2. If I put minus 2 here, minus 2, okay, let me do 5 is equals to a minus 2 plus b minus 2 plus 1, right? So minus 2 plus 2 is 0, and 0 times a is 0. So I have 5 still outside here. This is 0 plus minus 2 plus 1 is minus 1. Minus 1 times b is minus b. So b is minus 5. b is minus 5 for the first instance. b is minus 5 for the first instance. Let me just continue here. b is minus 5 for the first instance. Again, I go back to this expression. What will I do to this side to make it 0? I will say let x be minus 1. Again, I put it here. I say 5 is equals to a, open bracket, minus 1 plus 2, then plus b, open bracket, minus 1 plus 1. So here it becomes 0. Here it becomes 1. That's a, right? 5. So a is equals to 5, and b is equal to minus 5. So I've gotten what these two is. So I will come back here and put what my a is as 5 all over x plus 1, and my b as minus 5 all over x plus 2. So I've succeeded in splitting this thing into these two, this fraction into these two. I succeeded in doing that. Now, having done that, I'm going to now integrate. So my integration will now be easy. This integration I'm confused here will now become integral 5 over x plus 1, then plus integral minus integral 5 over x minus 2, or plus 2, sorry. So I've splitted it into 2. So this one is easier for me now to do. Remember, we know that this one here is a constant. I can bring it outside. This one, I can bring it outside. Okay, let me take this one off so that I can continue here. So at this point, bringing them outside, that's bringing this 5 outside. I have 5 integral 1 over x plus 1 dx minus 5 outside again, integral 1 over x plus 2 dx. Okay, so that's it. So now, from our standard integral, this is the same thing as saying 5 ln x plus 1 minus 5 ln x plus 2. Again, the minus sign here can make, this one can come be outside. So the minus sign is ln x plus 1 all over, minus the division, then ln x plus 2 plus c. So this is 5 outside, ln is together. So I have x plus 1, x plus 2, right? Then plus c. So this follows rule of mathematics, where you have 5 is common, is a common term here. That's why it's outside. And the ln too is also a common term. But because there's a minus sign in between the two terms that this ln logarithm is operating on, this minus turns to division. This is the answer, but this is a refined form of the answer. In case you are doing objective style questions where you need to pick the correct option from that answer. Okay. So general rule for partial fraction is that you need to resolve some fractions into the partial fractions. So if I have another case here, like let me call it case 2, for instance. If I have repeated linear factors, that is, if I have 3 over, for example, 3 over x, then open bracket x plus 2 all cubed, right? You see that this one now can be resolved into something like this: a over x plus b over x plus 2, then plus c over x plus 2 all squared. See, by the time you split it out like this, you can be able to integrate each of these fractions and get the answer. So each term is easier to integrate when you can split the function like this. Okay, so another case is reducible quadrats. Let me call this one case 3. That's reducible quadrats. Okay, so if I have 2x, for example, again 2x plus 5 all over x squared plus 1, right? So the denominator is a quadratic expression. We can split this to be something like this: 2x all over x squared plus 1 and 5 over x squared plus 1. So if you have done that splitting, then you can integrate separately, integrate the first term, use substitution, integrate the second term, you can get arctan of x. So let's just dive into trigonometric integrals, and we'll from there wrap up this particular video. So if you have integrals, trigonometric integrals, for example, sine square x, you have our trigonometric identities. So in general maths, you need to apply the identities even in this integration. Recall from our trig identities that sine square x is the same thing as 1 minus cos square x all over 2, right? 1 minus cos square, no, not cos square, 2x, yes. 1 minus cos 2x over 2. This is like an identity. It's something that has been derived from our trigonometric identities. So if I were to integrate sine square x dx, so I can split this into two parts. I can split this into integral of 1 over 2 dx, that is this 1 over 2, right? 1 over 2 minus integral cos 2x over 2 dx. Okay, so for this first part, the integral of half is x over 2, right? Then minus half can come outside now. Integral cos 2x dx, right? So this one is a composite. It's a composite. There's a function inside this function, right? So I'll be having x over 2 minus half. Then to integrate this one, it's the same thing as saying sine 2x over 2 plus c. So wrap it up, x over 2 minus sine 2x all over 4, because 2 times 2 is 4, plus c. So this is the integral of what I have on the board. Okay, so here's another case where we also apply trigonometric identities. If you have tan x dx, that integrates, you know that the identity for tan x is sine x over cos x, right? So I will now do this in this form, sine x over cos x dx. Okay, so remember that if we say let u be cos x, what? Then du dx will be sine x. That will be minus sine x, right? Okay, so if I come here and I inspect this, I see that I can write this as, okay, if du dx is equal to, so du dx, right? So I can still say du is minus sine x dx. Well, this one will go up and meet this one now. I want it to be on the straight line. Okay, so I'll say let u be cos x and du is minus sine x dx. Okay, so quickly substitute here. So I will still write this one again, like this. Instead of having sine x dx, I have du up there, but there's a minus sign here, right? And instead of having cos x, I'll be having u. Okay, so that minus sign in the same thing as saying minus outside 1 over u du. What I've written here is the same thing as what I've written here. I just move this minus outside, and there's a 1 on top here, then shift this one to so that it can look well. So here now, it's the same thing as saying minus ln u. But recall, we'll define u as cos x, right? So this one will now be ln u minus ln cos x plus c. So the integral of tan x is minus ln cos x plus c. So this is just the answer. But you know, you can also write this one like this. You can write this one like ln sec x plus c, because the minus cos x is ln x. So ln sec x plus c. So just go through the module again. I will leave some self-style questions, so TMA style questions on the comment section with sample answers. So I hope this video had been useful for you. I'd like to thank you for viewing.